Okay.
Speak up for the room. That's just me.
Good. Hi. Good afternoon, everyone. This, I think, is our first CUbit talk of the new year. I hope that's true. Our speaker today is Professor Nathalie De Leon of Princeton University. Nathalie received her PhD in 2011 from Harvard, working with Hong-Gun Park. Her PhD was had a few different topics involving molecular electronics and then plasmonics. She went on to do a postdoc with Misha Lukin, learning about NV centers, quantum sensing and quantum communications. And she now runs a lab in Princeton that kind of touches on lots of topics in quantum information science. She has won numerous awards. The, I think, exciting recent one is the 2023 Prize in Quantum Information, named after Rolf Landauer, the Landauer Prize. And I think today's talk is a new platform for quantum sensing and quantum computing. Go ahead, Professor De Leon.
Figure out how to navigate the two microphones. Thank you for the kind introduction and for the invitation. It's always fun to come visit friends at Gilla. I'll just mention really briefly that I noticed on the way in that my abstract got cut off on the posters, so I hope nobody thinks it's too much of a bait and switch, but the second half of this talk is about superconducting qubits. Okay, so a third of, broadly, my group works on 3 different areas, as Conrad mentioned. About a third of my group works on quantum sensing, mostly focused on trying to really push the frontiers in nanoscale quantum sensing using NV centers and Diamond. Another third of my group works on quantum networks, so integrated quantum nanophotonics and new solid state defects for trying to do long distance quantum communication. And then the last third of my group, this is a sort of newer effort that I've been working on since just before COVID on trying to find new material systems for quantum computing, specifically for superconducting qubits. So I had to down select significantly for this talk, so I will not talk about this middle topic, but I'll tell you one story about some new stuff that I'm excited about on the nanoscale quantum sensing front, and then I'll spend the second half talking about qubits. Okay, so the physical platform that we are working on for nanoscale quantum sensing is the Nitrogen Vacancy Center in Diamond. Sorry, I can't actually see my slides from back there. So this is a substitutional defect in Diamond. If I take the Diamond lattice and take 2 carbon atoms out and then put in 1 nitrogen atom, then I have nitrogen next to a vacancy. And it turns out that this little color center has very, very deep defect levels far away from the valence and conduction band edges of Diamond. And because of this, and because of the very large kind of band gap and headroom that you have from Diamond, you even have electronic excited states, orbital excited states that are also very far away from these band edges. So to first order, you can sort of think of this as like a little trapped molecule where you don't have to think about the extended lattice or the fact that it's a solid state object at all, but you can do all of the nice tricks that you do, that everyone here knows and loves, manipulating and reading out the internal degrees of freedom of this defect with light. So generally speaking, the reason that there are so many different groups that are working on NV centers in Diamond is because of the following properties. So the negative charge state of the NV center is a spin 1 defect. So in its ground state, you have a spin triplet. And it turns out that there's this very convenient mechanism for reading out the spin state even at room temperature. So with very unsophisticated lasers, like basically my green laser pointer, I can shine light on this defect, and if I start in ms equals 0, I have a pretty good cycling transition, so it'll just keep on scattering photons and coming back to ms equals 0. But if I'm in plus or minus 1, I have this spin-dependent intersystem crossing to a dark state. And this thing lives about 10 times as long as my excited state lifetime, so it effectively changes the number of photons I can scatter off of this defect in a spin-dependent way. So you can use this to read out the spin state of the defect. You can do optically detected magnetic resonance. So here I'm changing the microwave frequency as I go over the zero field splitting. And you can see this little dip in the total number of counts. And you can do things like just read off the local magnetic field by looking at Zeeman splitting. And then you can do coherent manipulation of this ground state and then this optical readout to figure out what it is that you've done. And then importantly, because you're in diamond, which has very low density of states for phonons, it's a very stiff lattice, and these are all very light atoms, you can actually have a very, very long spin lifetime even at room temperature. So at room temperature, the NV center has a T1 of something like 10 milliseconds. And the coherence time is just limited by the number of nuclear spins in your vicinity. And fortunately, carbon is mostly carbon-12, so you don't have that many nuclear spins. And you can do things like isotopically purify the environment to get really, really long spin coherence time. So people sort of routinely work in the many milliseconds range, even at room temperature. So that's what makes this very special. So based on that set of properties, there's been an enormous amount of activity in trying to use these things as sensors. In general, the way that you can think of it as is, I have some, let's say if I would just plot contours of dipolar coupling as you move away from this NV center, you can see that they change very rapidly, as you would expect from something that looks like a point sensor. So you can do things that look a lot like magnetic resonance imaging, but now on these nanometer or even angstrom scales. And because you have a single spin that's really localized in space, you effectively make something that has the largest possible magnetic field gradient, right? And that really gives you this really amazing spatial resolution. So there have been, a number of efforts trying to push the frontier of looking at, for example, single molecules external to the diamond. There's this beautiful work where people take small volumes of liquid and do nanoscale NMR, much like a multi-well plate type experiment in a microbiology lab. And then there's also a robust community trying to use NV centers to do condensed matter sensing. This is an example from Patrick Malatinsky's lab in Basel, where they have a scanning tip with an NV center in it, and they can look at the magnetic domains in, for example, a 2D magnet. This is chromium triiodide, and they were able to learn things about kind of the nature of magnetism in this sample. So just to show you sort of the promise of this probe, there's this beautiful work from Tim Tamenyau's group from a few years ago, where they were able to push this almost to its logical limit. They have an NV center that's deep in the bulk of diamond, and they do some pretty complicated NMR pulses actually to look at different carbon-13 nuclei in the vicinity of the NV center. And they use this to do magnetic resonance imaging of each of the positions of these carbon-13 nuclei. So they're able to look at the positions all the way down to this kind of sub-angstrom resolution of, I don't remember exactly how many it is. I think it's in the title of their Nature paper. It's like 27 carbon-13 nuclei or something. So I think it's pretty clear that if you could do something like this, but for random targets, not things that are just deeply embedded in the diamond, that this would be a very powerful tool that would really change, just what we're able to do in terms of nanoscale sensing. All right. So here's the dream. You take an NV center, you have some sensing target. This is a physicist protein, right? A little blob of nuclei. And now in order to be able to see it and to be able to get this exquisite resolution and sensitivity, you need to get very, very close to the sensing target, right? Your interaction is going to look like 1/r³ or 1/r⁶. But also it's sort of obvious that you need to get very close to be able to take advantage of this really high spatial resolution. So the problem is that while these NV centers deep in the bulk of diamond can be really exquisite, when you get close to the sensing target, you also have to get close to a surface. And in general, I would say that mankind is quite bad at surfaces. And in particular, we are really, really bad at diamond surfaces because diamond is the hardest material in the world. So even doing things like polishing, and just preparing a nice surface are very non-trivial. So one of the ways that we know that this is a big problem is that if you just look at NV centers and map out their coherence time as a function of depth away from the surface, you see this horrible power law scaling as you approach the surface. I wouldn't take this scaling too seriously, but it's something like 1/r⁴. So while we have these coherence times of milliseconds when you're in the bulk, you get to within, let's say, 100 nanometers of the surface and you see this terrible crash. And when you're within a few nanometers of the surface, it's more like less than a microsecond. Okay, so when I started my position at Princeton, we set out on this somewhat crazy project to try to understand this surface noise in detail. And the challenge here is that, the NV center is a very sensitive probe, but it's really non-selective. If you measure the NV center, it just kind of tells you, my T2 is lousy. And you can take it one step further and ask, is your T2 lousy in this frequency regime or this frequency regime? But that's pretty much it. It doesn't tell you anything about the microscopic origin of what you're staring at. There are a bunch of ways to do surface science, right? You can just look at the surface directly and try to learn things about that surface. In general, these techniques are quite challenging. There's a lot of technical problems when you look at carbon in particular, and diamond is very insulating, so that causes issues. But I would say that there's an even more fundamental problem, which is that a priori, you have no reason to expect that the surface spectroscopy is going to give you relevant information because the NV center is probing this very tiny area, right? It's basically just looking at its nanoscale environment, whereas the surface technique is looking at much, much larger areas with much lower sensitivity. So whether or not you're actually going to find anything that correlates appropriately with your NV center is sort of up for grabs. So I did the dumbest experimentalist version of this project, which is let's just try lots of things, right? So let's look at many different surface spectroscopy techniques, figure out whether or not there is a difference between surfaces where we know that the NV centers look different, and then find a correlation, use that to develop a microscopic hypothesis, and then pull on that hypothesis. That's the general approach. So we did this sort of alphabet soup of different kinds of surface spectroscopies. And everything in gray is stuff that didn't really give me useful information. So you can see, and many of these things were, synchrotron runs. So this was a big investment. But then, in the end, we sort of zeroed in on a few photoelectron spectroscopy techniques, X-ray photoelectron spectroscopy, ultraviolet photoelectron spectroscopy, and near-edge X-ray absorption fine structure spectroscopy, which gave us useful information from the point of view of this problem. And then what we could do is go one step further than just asking the NV center, are you happy if you're doing your time lousy? You can do a few things with this nanoscale spectroscopy, basically applying different pulse sequences to learn a little bit more about the nature of the noise that you're staring at. So I'll cut an extremely long story as short as possible because I don't think any of you want to listen to a 3.5-hour long lecture about surface science and diamond. And I'll just tell you a few sort of illustrative pieces of the story. So the first is that we sort of immediately discovered that the whole community was using oxygen-terminated diamond to make charge stable NV centers, but what you call oxygen-terminated varies drastically depending on what exactly you did. And more to the point, you could do the exact same sort of chemical treatment to different surfaces and get drastically different surfaces. So for example, oxygen etching of diamond tends to be very hysteretic. So extremely small differences in the surface quality to begin with can lead to drastic morphology differences at the endpoint. So these are two things that went through the same process, but one of them has the fancy polishing and one of them has the less fancy polishing. And you end up with these, giant kind of hills and valleys. And we could see a direct consequence in the X-ray absorption spectroscopy in the electronic structure. So this is NexAFS, which is basically a probe of the unoccupied density of states. This sharp peak here is the exciton edge of diamond. So everything to the right should be there. It's the conduction band structure. But then everything to the left is just defect states. And you can see that for this rough surface, you have this huge density of defect states that are near the surface, which are suppressed for the smooth surface. So using these kind of tools for feedback, we could then come up with a somewhat labyrinth process for creating pristine surfaces in diamond. And again, I'll spare you a lot of the pain of listening to what we had to do, but the general idea is, we start with this state-of-the-art low damage surface polish. We do reactive ion etching to remove the polish damage. That leaves behind a different kind of damage, so we have to remove that with a different sort of etch. That leaves behind its own damage, so we do a thermal anneal to remove this last kind of gentle surface layer. And then finally, we do this oxygen anneal to make a chemically nice surface. Spiritually, this is like you have a mouse problem, so then you release the cats, and now you have a cat problem, so you release the dogs, and you keep on going until the gorillas die in the winter. So that's the general idea. So we can do a little bit more to understand this by zeroing in on the comparison between these two last steps, okay? So if I look at, so I'm going to call this the acid clean surface and the oxygen annealed surface. So if I look at NV spin coherence between these two surfaces, you can see that the Hahn echo T2 gets increased by about a factor of 2 or 3 with this last step. We can also do dynamical decoupling to probe how this T2, or what the frequency of this noise bath looks like, and we can see that we get this improvement across a very broad bandwidth. We can also do some tricks, like take advantage of the fact that the NV center is a spin 1 defect to do relaxation spectroscopy. In general, these single quantum transitions can be driven by magnetic noise, whereas these double quantum transitions require electric field noise. So the differentials between these tell you something about whether you're looking at magnetic field noise or electric field noise. And then we can kind of make our best attempt at a parameterization where we can plot these in a unified plot. And what we see is that we have a very broadband magnetic noise bath, whereas our electric field noise, if we just extrapolate, is lower than our magnetic field contribution. Okay, so that's from the point of view of the NV center, and then we can look at the surface spectroscopy, and what we see is, if we look at this X-ray absorption spectroscopy and the oxygen edge, sort of to my disappointment, these things look broadly similar. I think surface scientists hate it when I put it this way, but I have a peaky thing here and like a shoulder thing here, and it's essentially the same here. But the drastic difference between these things is that if I do a polarization dependence, you can see that it's completely washed out for this acid clean sample, whereas the oxygen annealing gives you this huge change in intensity as I change the polarization. So the general picture is that these things are actually chemically quite similar, but there's a much higher degree of disorder before you do this last step. And this disorder even leads to really big electronic consequences, like we can do ultraviolet photoelectron spectroscopy, which just probes the electron affinity, like the position of the conduction band relative to the vacuum level. And we see something like a 1.5 eV shift between these two surfaces. So just this degree of disorder is enough to really, really change where these bands lie. Okay, the punchline is that by doing a lot of this work, we're able to extend the coherence time of shallow NV centers by around an order of magnitude. So all of the points that I showed you are here sort of grayed out. And then now with our best processing, we can get to 5 nanometers from the surface with 10 microsecond coherence times. And then importantly, we can dynamically decouple out to something like 200 microseconds. So we now have very nice coherent shallow NV centers. Okay, so this is a slightly old story. So my group now just routinely makes these nice substrates that have coherent shallow NV centers. So since then, what we've been working on is actually using them as sensors. So there's sort of 2 big efforts in my group. One is on deploying these things as a platform for biophysics, and then the other is miscellaneous physics, which is now what I'm going to talk about as recent work. So the question that we started asking sort of around COVID was, let's say instead of just using the NV center to look at the magnetic field at a single point, you instead look at multiple NV centers simultaneously and then look at correlations in the magnetic field. Is there more information? Is there different kinds of information that you can learn if you do something like this? So just to set it up, for example, I'm going to put traditional in scare quotes because obviously this field is only like 10 years old. But the traditional imaging would be, let's say I have some condensed matter system of interest. In this case, this is work from Misha Lukin's group where they put graphene on top of a diamond, and then they're looking at transport signatures in the graphene. And what they're essentially doing is looking at individual NV centers and doing noise sensing, in this case, that arises from electron-phonon coupling during transport. Okay, and most NV sensing is some variation on this theme, where you're either looking at the magnetic field projection at a single point, or you're using the NV center to learn something about the noise environment. Okay, so the idea here is now let's just take 2 NV centers, measure them simultaneously, and then try to look for spatiotemporal correlations in this noise. And this is work, again, because we were all at home during COVID, it was easy to collaborate remotely. So we started this collaboration with Shimon Kolkwitz's group at University of Wisconsin-Madison. And I'll just mention right at the front that this was all led by my postdoc, Jared Rovney. Okay, so the setup is I have 2 NV centers, and each of them is staring at some kind of correlated noise bath of interest. And then they each have some uncorrelated noise that we don't have control over, usually things like nuclear spins or electron spins that are in the vicinity of the NV centers. Now, what we can do is basically just a Ramsey experiment. So we take both of the NV centers and put them on the equator of the Bloch sphere, let them accumulate phase, and then now, in order to look at correlations, what we want to do is instead of just doing a population measurement directly back onto the z-axis, what we can do is a pancake pulse where we flip it like this. Now that gives you maximal sensitivity, but you would normally not want to do this for single NV measurements because then all of your measurements would average out to 0. But now, because we're looking at this higher order moment and we're looking at this covariance, this is the thing that you want to do. Okay, so otherwise this is all the same as what everyone would do, but this is a Ramsey where we do this and then let the things fan out and then flip it like this. And then the idea is we now save all of the traces, save all the data, and then we just compute a correlation between the two different NV centers. All right, so what do I mean by computing a correlation? There's sort of a, what did you do with your being stuck at home during COVID? I learned Bayesian statistics. So this correlation is going to come from some underlying phase distribution in the two NV centers. And then on top of that, of course, you have some quantum projection noise when you actually do this final measurement. And then you have some readout noise, right? And that's going to give your total Pearson correlation at the end. Now, the problem is that with NV centers, normally you get extremely few photons per shot. So it's something that people don't like to talk about because it doesn't sound great, but you basically get something like 0.03 photons every time you run an experiment. Now, you can run these experiments every 10 to 20 microseconds, so you just average 1 million times, and that's how you do these really beautiful quantum measurements with NV centers. But now, if you're doing something like computing this Pearson correlation, this readout noise is really killer, right? And you can sort of see that intuitively here. If I just do this conventional readout with two different NV centers, the chances that I'm ever going to see a coincidence between two of them is very low. So I'm just going to have to wait forever to be able to see some of this correlation. So we had to turn to something that would give you improved readout fidelity. And what we did was we employed spin to charge conversion. So this was actually work that I was part of when I was at Misha Lukin's group that was led by Brendan Shields at the time, where what we found was that if you just applied a very intense ionization pulse, because because you have this spin-dependent shelving in this shelving state, you basically also get a spin-dependent ionization. So you can sort of map spin equals ms equals 0 to one charge state and ms equals plus minus 1 to a different charge state. And the reason you would want to do that is it's actually very easy to read out the charge state because these things fluoresce in totally different bands. So all you have to do is sit there and count photons in the right band. And it turns out that you can get much, much higher fidelity measurements. But the reason that you would not normally do this for magnetometry is that these readout times are really long. You're talking about something like a millisecond. So even though you improve your readout fidelity, you really increase your overhead, and then this is not a trade that you would want to make a better sensor. However, here we care about readout fidelity to the 4th power. So now you really, really are willing to make this readout fidelity trade for overhead. And the way that you can kind of quantify this or parameterize it is you can think about some sort of minimum, little noise signal that you can look at with this covariance. And how long does it take me? This is sort of like a sensitivity plot. How long does it take me to get to an SNR of 1 for some total experiment time? So sigma r equals 1 here is the quantum projection noise limit. Conventional readout is at 35 times the projection noise limit, and you have something like this, where to get to a 1 nanotesla signal, you are integrating for 1 million seconds, which is an unacceptable fraction of a PhD. So if we do this spin to charge conversion, we can get to within a factor of a few of the quantum projection noise limit, and then you're now looking at the thousands of seconds, which is a painful experiment, but an acceptable fraction of the duration of a PhD. Okay, so we set out to do this spin to charge and actually implement this correlation sensing, and it's relatively straightforward. You just have to build a dual channel, confocal microscope, and then find some way to, mount your diamond and apply some other noise signal with an antenna. And the thing that we found sort of immediately, I'm saying this as a community service in case anyone wants to actually build one of these experiments, is that you measure a lot of trivial correlations basically right away. So, we started and we did the experiment and we got this data point up here and we were like, great, we see a correlation. But then because you save all of this data, you can just sort of point shift your data, right? And then see if there are correlations that show up anywhere else. And we saw this clear sort of periodic behavior. And actually, we somehow found this out from June's lab that your table can be floating, but then not really floating, and you have a little touch on one of the legs. Don't remember who told us that fact. But we then went hunting for that, and were able to sort of beat down all of these spurious correlations. So it's much harder to build a 2NV experiment than a single NV experiment, but after a lot of pain, it is possible. So here is now an example of detecting correlated noise with 2NV centers. So this is a scanning confocal microscope image. Each of these bright blobs is a single NV center. We can pick out 2 NV centers and then now do this measurement. So this down here is data where we are binning conditioned on measuring 0 photons in NV1. Do we see 0 photons in NV2, or do we see a bright NV1 or bright NV2? And you can see that there's no correlations, essentially no correlations when you don't expect there to be. And then if we apply this correlated noise, you get this nice checkerboard pattern, which shows that when NV1 is bright, NV2 is bright. And then because these are spins, we can just do this trick where we also prepare them on opposite sides of the Bloch sphere and do the exact same experiment. And what you should see is an anti-correlation. And you see that this checkerboard pattern nicely just flips. So what we've done here is just applied some 2 megahertz signal, and we can put in this x/8 pulse that, where we sweep the time delay to become maximally sensitive to this 2 megahertz signal or minimally sensitive. And you see that we can kind of nicely resolve this feature in frequency space, and that we see a perfect mirror symmetry with the anti-correlation, which shows that we're really sensing this magnetic correlation. And the magnitude of this correlation here is basically just is 1 over the readout noise squared. So it quantitatively matches what we expect. Okay, so what can we do with it? So one of the things that we can do is disentangle different sources of noise. Let's say we had 2 sources of noise where one was correlated and one was uncorrelated. If we were looking at a single NV center, we would basically just do some coherence measurement. We'd see a couple of dips and then transform that into a spectral density of the noise and see 2 peaks. And then if we do this covariance detection, what we should see is that only the correlated noise shows up in covariance. And then now we can label these 2 peaks as being either correlated or uncorrelated noise. And it turns out that we're able to do that pretty easily. So here are 2 NV centers in orange and gray. They each have 2 different peaks when you just do this kind of traditional variance measurement. And one of these peaks is the global signal that we've applied, and the other one is just from local nuclear spins. So in general, these local nuclear spins should not give you a correlated noise signal. And then when we look in the covariance channel, you see that only one of the peaks appears. So it's clear that this is the correlated noise and this is the uncorrelated noise. The other kind of interesting case that we can look at is that if we apply a very strong white noise signal, we can artificially shorten the coherence time of both NV centers so that they now have a coherence of a few hundred nanoseconds. And normally, if you were trying to do something like nanoscale NMR of these nuclear spins, you would need to operate up here where you still have some remaining coherence. But now, all the way down here in the noise, where you don't have any remaining coherence, because this noise is all correlated, it's white noise that is applied to both of them, it's common mode. Now, if we look in the covariance channel down in here, you can see a little NMR dip that comes from the nuclear spin peak. So this is maybe not dissimilar from the kinds of tricks that people here have been playing with clocks, where you can look at differential channels and then use that to eliminate the common mode noise from your laser. Yeah, Adam.
So the correlated signal you're looking at is subtracts off the first order moments, right?
Yeah, that's right.
So why in that signal would you see correlated noise?
Because it destroys the correlation, right? So you have some noise, some added noise that is now no longer correlated.
Oh, that makes sense. So
Yeah.
You're just saying that to have sufficient signal noise in your correlator, you need to get rid of this one, the uncorrelated noise. It's not that the uncorrelated noise creates a signal in the correlator.
No, it's that the uncorrelated noise destroys your correlation. So then you see it as a little dip. But that's the same as when you do this normal, coherence measurement. You're looking for a little destruction of the coherence, right? So you would normally be looking for a little dip. Okay, the last trick that we can pull is that now let's take two NV centers that have different orientations with respect to the magnetic field so that they have different spin resonance frequencies. Now we can have independent control over the two NV centers and then use that to set a time delay between the two NV centers. So now I start the clock on NV1, wait some time, and then start the clock on NV2. And in doing this, now if I have this kind of signal where shot to shot it's phase random, if I just plot this correlation as a function of time delay, I can still reconstruct that that the signal is coherent within this time window. Okay, so even though this is averaged over something like an hour or a few hours of averaging, and the phase is totally random across shots, because I have this, it's sort of like a pump probe measurement, I can basically reconstruct the coherence on short timescales. And then similarly, I can use this as a probe of dynamics at these timescales. So now if I really randomize, if I add some noise to this phase so that the phase noise destroys your coherence in under a microsecond, this is not something that you would normally be able to see with an NV center because the total overhead of your sequence is something like 10 to 20 microseconds. But now, because I can just sort of set the time delay arbitrarily between these two NV centers, I can see this dephasing on these very short timescales. Okay, so what I have shown you is essentially a method for measuring a 2-point magnetic field correlator at 100 nanometer to 100 micron length scales, and let's say tens of nanosecond kind of time scales. And this is not something that is physically accessible with any other technique, as far as I can tell. And the place where this, I think, is really powerful is in characterizing condensed matter systems, because there are actually a lot of phenomena that you would be able to characterize instantaneously if you had access to this 2-point correlator, but nobody has access to this 2-point correlator, so instead you do these really labyrinth experiments to try to capture something that is effectively the same as this 2-point correlator. So we're now really excited about this direction and have started building a number of experiments. One is looking at relativistic hydrodynamic flow in 2D materials, where there has been a lot of beautiful work that is suggestive that you see hydrodynamic flow and that you can go through this phase transition, but it's very hard to do quantitative work. So we've started collaborating with Saranga Balakrishnan on how to calculate these things. So we don't know exactly what to expect, but I know that if you go from a Fermi liquid to something that has the viscosity of honey, that's got to change. That's got to change the correlations in the noise. And then there's a lot of other interesting work on trying to characterize quantum spin liquids and other kind of magnetic dynamics, where I think these 2-point correlators can be very powerful. Okay, so just to conclude this section, we have come up with a way to make NV centers within 5 nanometers of the surface with 100 microsecond plus coherence times. And we are now using these in combination with this nanoscale covariance magnetometry technique to try to study spatiotemporal dynamics of a variety of targets. There's a lot of other work going on in my group trying to understand these shallow NV centers that I didn't have time to talk about today. We have this ultra high vacuum confocal microscope where we're able to make new surfaces and then probe them in situ without breaking vacuum. I think this is the only UHV cryogenic confocal microscope in the world. But I think if you take away just one of those words, it's no longer the first. But these are now single NV centers in this UHV system. And then we've also started thinking about now not ignoring the surrounding diamond quite as much and looking at things like itinerant carriers, traveling along the conduction and valence band. And what we see is interesting phenomena, like if I pump this NV center, then I can see a change in the charge state of this other NV center that's surprisingly far away, like many microns away. So we can really see these itinerant carriers traveling extremely long distances in this ultra high purity diamond. And then, of course, we have a big effort in the group to actually use shallow NV centers. So we have some work looking at spin dynamics in the diamond and of external targets, and some other work trying to push the NV center towards nanoscale NMR of single molecules. All right, so I will pause there for questions because I'm going to drastically change gears. Jude.
Just a quick question. When you do this NV center correlation, how many pairs can you do that simultaneously?
Yeah, that's a good question.
To create a map.
Right. So far, with our proof of principle experiment, we did the dumbest version, which is just a beam splitter or 2 APDs. But I don't think that there is any fundamental reason why you can't image on a camera and then now look at many NV centers simultaneously. And the idea there would be that and actually the spin to charge is very nice for that because we now have this, millisecond kind of scale readout, so it's sort of compatible with cameras. And then the idea there would be you just look at all the NV centers at the same time, and then at the end compute any pairwise correlation you want.
In that situation, do you have to worry about NV center interactions, or instead of now measuring the spatial temporal correlation of magnetic field, you could also now have the interaction effects of things?
Yeah, so it's easy to make them not interact because I can just I guess you can see here, right? These things are optically resolvable, so they're at the hundreds of nanometer scale. I think it's an interesting open question whether there's anything you could learn if you did make them interact.
Yes.
And we have been thinking about whether or not some of these techniques are compatible with like subdiffraction limit imaging, but haven't figured it out yet.
Thanks.
Yes.
Maybe a very naive question. Since you were mentioning that diamond is an insulating material, it's not electrically conductive, how do you do the UPS? Are you not worried about like charging up, messing up the signal?
Yeah, so we are worried. And for those experiments, we actually have to use lightly boron doped diamond. Okay, so now I will totally switch gears and talk about the other experiment in my group, which is trying to improve the lifetime of superconducting qubits. So superconducting qubits are a very successful platform that is now the basis of some of the largest quantum processors. If I sound like I'm not part of this field, it's because I'm kind of not. So I'll just give my 37,000 foot view of things. There have been a number of sort of beautiful experiments that people have done with these large scale processors, like this nice work out of Google. I should probably remove this, but where they're doing quantum chemistry, quantum simulation, some interesting many body physics, and there's this big march towards trying to build a fault tolerant processor. Sort of hidden under the hood of all of that beautiful work is that if you look at the coherence time and lifetime of superconducting qubits over time, like a Moore's law plot, the field has been pretty stagnant since about 2012. So people reached 100 microsecond transmons and then just have not been able to push the bar since then. And it's generally believed to be limited by dielectric loss. So there are a couple more things that we know about these losses. So the first is that if you look at the bulk constituent components of the system, you should get much, much longer lifetimes, but you don't. And then the other thing that we know is that if you make the devices smaller, they get worse. So this points to interfaces and surfaces as being a critical source of loss in these devices. The other thing that people know is that the losses get a lot worse at low temperature and low microwave power. So what you see, this is now a plot of the loss tangent as a function of temperature and as a function of microwave power from Janson Gao's thesis. And you can see that the loss goes down with temperature and also goes down with microwave power. And this is very weird because normally if I just give you a chunk of something and ask you to characterize its losses, it should just be linear. Right? But here what we're saying is that you increase the microwave power and you get lower losses, so you have something that saturates. And this is why people talk about two-level system loss in these kinds of systems. So there's a number of candidates for this loss and noise if you just kind of stare at a transmon. You have the substrate surface, and you have the device surface, and you have kind of funny physics that can go on in this Josephson junction. So one question is, how do we zero in on where this loss is actually coming from and which surfaces are important? So we got, I ran around giving this NV talk for a few years about how we systematically figured out what was going on at the diamond surface and how to improve NV centers. And at a large number of these conferences and seminars, people would sort of come up and say like, oh, did you know that trapped ions also have anomalous heating rates? Maybe you can come and solve the problems with trapped ion traps. And the superconducting qubit people would say like, did you know that there's this dielectric loss problem at surfaces? And I would just say like, look, those are your problems. Those are not my problem. I'm not going to be some sheriff that comes into town like solving everybody's surfaces. But then Andrew Hauk is sort of upstairs from my office, and I had this longstanding collaboration with Bob Kava, who is a solid state chemist, and I ended up just getting nerd sniped into this problem. So it is an interesting problem, and we formed this fairly large team. So this is all the work that I'm going to talk about is in collaboration with Andrew and Bob, and a number of people in my group and a number of people in Andrew's group. As well as postdocs in Bob's group, and this really crack team of undergrads actually over the years. Okay, so with Andrew and Bob, we started looking at Andrew's qubits and asking what could be wrong with these things. So his qubits were niobium on sapphire, and you have aluminum oxide in the Josephson junction. So there were sort of two basic hypotheses for where this dielectric loss could come from. My bias is that everybody has hydrocarbons all over everything, and substrate contaminants play a really big role. And then the other thing that we zeroed in on is that niobium oxides are actually quite complicated and really hard to control. And you can have resistive loss from weird kind of metallic or almost superconducting phases, and then of course a lot of dielectric loss from just very messy oxides. And Bob actually pointed this out by saying, I spent a very large fraction of my career in the late 80s studying the oxides of niobium, and that stuff just looks crazy if you look at it funny. So there's no hope of controlling this material. So we had two remedies for these two problems. The first was just look at your substrates and then try to make them better. And indeed, we could see even just with AFM and X-ray photoelectron spectroscopy that there were a large number of contaminants on the sapphire that we were staring at, the as fabricated devices. And you can do things like clean and prepare the surfaces and anneal them to recover these nice step edges on the sapphire and make sure that you don't have any of these heteroatom contaminants. To get rid of the niobium problem, we switched one down on the periodic table and used tantalum. Tantalum is a refractory material that is much more chemically resistant, so you can kind of throw it in a lot of different things to clean off the surface and fix your fabrication errors. And most importantly, it has a very nice stoichiometric oxide. There's one trick, which is that if you just naively deposit tantalum, you get the wrong phase. You get the beta phase, which is a tetragonal phase, whereas the bulk phase, which has a much higher TC, is a BCC alpha phase. And we didn't figure this out. Dan Prober figured this out a long time ago, but it turns out that if you just deposit at a hot temperature and you deposit fast enough, you can promote the alpha phase growth. So we see this nice epitaxial growth, and then as promised, if we zoom in on kind of this amorphous oxide layer, we do get predominantly Ta205. It's sort of always 2 to 3 nanometers, almost no matter what you do to it. You just get this kinetically limited stoichiometric oxide. And this oxide looks very robust to differences in microstructure and sputtering conditions, so really no matter what you do, you always get the same oxide. And the headline result is that by doing kind of this simple swap and being careful about our fabrication and cleaning off the substrate, we were able to routinely get lifetimes exceeding 300 microseconds, so about a factor of 3 over the previous state of the art. And this is a very robust result. So we see this on essentially every single device that we make. And I should say that since then, this essential result has been reproduced in many labs. So there's a group in the Beijing Academy of Sciences that has gotten T1s up to 0.5 millisecond or quality factors up to around 10 million. The IMEC group has been making tantalum on silicon resonators where they're able to see Qs of something like 5 million. And then most recently, Michel Devereux at Yale has used a tantalum qubit in their GKP encoding, their GKP code experiment to get real-time break-even quantum error correction. And there were many advances that led to this result, but at least one of them was that they switched to a tantalum qubit with a T1 of almost 300 microseconds. Okay, so that was a very exciting result because we were able to push the state of the art of what was possible just with this fairly simple material science. So since then, what we've been doing is systematic studies of what is responsible for the remaining losses in tantalum. So for this, we're making tantalum resonators to sort of eliminate the complications from the Josephson junction fab. And then the idea is that these films are actually quite robust to processing, so we can do a lot of stuff to it and then look at small changes in the losses as we do all of these different types of processing. And then, of course, you have the possibility of doing multiplex measurements because you can put lots and lots of resonators on one feed line and then just look at them in a spectrally selective way. Okay, so what we were, I'll just say, full disclosure, I came into this saying, everyone talks about two-level systems. I bet it's not two-level systems because it just seemed too easy, but it's all two-level systems is going to be the punchline. So what we can do is just a transmission measurement through one of these resonators. And we see this very two-level system-like behavior where the quality factor of the resonator saturates with increasing microwave power. And then I'll just mention as an aside, because I think this is interesting to a few people, that our high power Qs now are around 2 × 10⁸ for our best devices. So we actually have quite a bit of headroom to look for really subtle sources of loss, right? If our high power Qs were down at 10⁶, then we would have no hope of being able to monkey around with this low power stuff. Okay, so we can so this is a power dependent curve. And we can take this one step further and do a temperature dependence of the power dependence. So basically, at each vertical slice is one of these power dependencies. And then we just do one of these power dependencies at many, many different temperatures. And then what we can do is just take our loss model seriously and then try to fit all of the data. So we say that our quality factor is a sum of the TLS component, the equilibrium quasi-particle loss as you go to high temperatures, and then something that is power and temperature independent that we don't see in this data that stops you from getting to a Q of infinity at high power. And this all gives you something like 7 free fitting parameters, and we can just fit this entire data set and get a quite beautiful fit to the whole data set. And the nice thing about this is that what we can extract is something that we're calling here QTLS naught, which is a prefactor on the TLS related loss. And that now feels a lot like a material parameter, right? Because you now have something that is basically just the linear absorption associated with TLSs. And I can now take that and use it as a basis for comparison across many devices. So let me just quickly walk you through, I know this is a somewhat complicated plot, but basically at high temperatures, what you have is you break up Cooper pairs. So you just see quasi-particle loss and no power dependence. In these intermediate temperatures, you see a lot of two-level system loss, so the powers are very different. And then this kind of gentle slope up is this hyperbolic tangent part that just comes from the partition function. So you just thermally saturate your TLSs, and then that saturates the loss. And then this interesting little downturn right here is actually predicted in Jansson Gau's thesis, which is, as far as I can tell, like the Bible of this physics, which is that if you have TLS interactions, then you can get a 1/t scaling to the TLS coherence time, and then that will change your saturation parameter accordingly. So basically at low temperatures, it's easier to saturate your TLSs, and you get this little upturn. We can also do an independent measurement of this TLS loss by looking at the frequency shift with temperature. And then we can look across many, many different devices. What is the QTLS naught extracted from one method versus the other? And we find that we get pretty good agreement. So I think this is a really robust comparison, a robust parameter to do material comparisons. Okay, so the next thing that we can do is make many different devices that are different sizes. And the general idea is that, I pull my capacitors apart, and then that blows up the mode, and then the fraction of the field that overlaps with a little layer of surface goes down, right? So I just changed the surface participation. And what we see is that as you change, so this is, I know this is very confusing, but the devices are getting bigger as you go to the right, so the surface participation is getting lower. That's why it's in this weird inverted axis. But as you make the devices bigger, they get better. So you get this quality factor scaling that goes up. But then interestingly, for the largest devices, everything kind of plateaus. So you have something that's creeping in here that is no longer surface dependent. And then we can do things like compare two different surfaces that you prepare with chemical processing. So these are our native oxide samples, and then we can do a really standard trick in silicon processing, which is dip the whole thing in buffered oxide etch to try to pull off a little bit of the oxide. And you can see that, okay, there's some scatter in the fab, but in general, the blue points are all about a factor of 2 higher than the orange points. So we see this increase in the surface-related QTLS not after the surface processing, but then these things are really overlapping up here. And then we can take it a step further and do different types of BOE dips, and also this crazy thing where we boil it in a mixture of nitric perchloric and sulfuric acids to try to increase the oxide thickness, and then basically extract out all of these different surface loss tangents. And what we generally find is for our best devices, we have this surface loss tangent that's something like 7 × 10⁻⁴. And then the only way to make all of this data make sense is that there's also something that looks like a bulk substrate loss tangent that's at 1.5 × 10⁻⁷. And this would not be possible unless you really explored this giant parameter space. Okay, so this is now a plot of that surface loss tangent, and you can see that this BOE decreases the surface loss by a factor of 2. The other thing that's a little bit surprising is that this triacid data line, which is the green loss tangent curve, has an oxide thickness that's about a factor of 2 larger, but you can see that these points didn't go a factor of 2 down. So we have an oxide-related loss that is not extensive in the oxide, so you need to invoke at least one other TLS path. So one possible model is that we have oxide and hydrocarbons, and then both the BOE and the triacid are really good at getting rid of these hydrocarbons, and then they kind of they sort of cancel each other out, basically, that you increase the oxide loss and decrease the hydrocarbon loss. Okay, so our current understanding, that probably went by too fast, but the takeaway is that our current understanding of the losses in state-of-the-art devices is that we have this surface TLS that looks like this, a bulk TLS that looks like this, and I didn't show you any data at all, but we also think that our Josephson junctions are now worse than our best resonators. So it is now time to revisit the Josephson junction. And then I'll just mention our packaging loss is way up here. So we have a lot of headroom to continue to improve. Okay, I'll just mention really quickly that everything that I showed here is the linear susceptibility. So it's sort of extracting this QTLS knot, but that's not actually relevant for device performance. Device performance happens at an average intercavity photon number of 1. So what you really want to look at is how good is your Q at this average intercavity photon number of 1, and we get Qs of around 10 million, basically 10 to 12 million in our best devices. Okay, so I promise this will take 3 minutes. But now, so we've done a very systematic job of measuring a lot of tantalum resonators, so now we can go back and say what is actually going on with these oxides. And the method that we came up with to look at this is to look at chemical profiling with X-ray photoelectron spectroscopy. And the general idea is that if you go to a synchrotron, you can change the energy of the incident X-rays. And for very low energies, you're mostly probing the surface because the bulk doesn't have, these electrons don't have enough energy to get out. And then at high energies, you're changing the proportion of the surface to the bulk. So by scanning the energy, you can generate a profile of what's going on in depth. So in order to build up this profile, this is an example of looking at the tantalum peak. So at very low energies, these two peaks are the oxide, these peaks up here are the metal, so you can see you mostly see oxide. And then at high energies, you mostly see metal. So this is showing the changes in depth. And okay, so there's a lot of peaks under here that all correspond to different chemical states of the tantalum. And I was a real XPS skeptic going into this project because there's just a mess down here. And then the question is, how do you know that it's like 4 peaks and not 8 peaks or 6 peaks? And how do you know where they are? And the kind of nice thing about this variable photon XPS is that you can fit your entire data set simultaneously and then get a lot more confidence that you have the correct number of peaks, right? So if we know that the same peaks have to appear at every single energy, and we take 50 different energies, now I have a very highly constrained search. So maybe for the first time ever, I am pretty confident at the number of peaks in this mess down here. So then we can use that to build up a depth profile of all of these different species. So red here is the oxide. So you can see that it goes down with energy as advertised, and then the metal goes up with energy. And then there are all of these little interface and suboxide peaks down here. And if you zoom in, you can see that the signal goes up and then goes down, which is what you would expect if they were at an intermediate depth, right? And then now we can take all of this data and use that to actually generate a depth profile. So we can basically put in trial functions to figure out where all of these species are, and then look at the comparisons between the native oxide, this BOE dipped sample, and the triacid sample. And okay, there are a few things that we can extract from this, like just the total amount of each of these species, but we can also look at things like their total distribution throughout this layer. And one kind of interesting thing that popped out of this analysis is that we had assumed from our resonator measurements that in order to explain the data, you need to invoke this separate TLS bath from the hydrocarbons. But actually another possibility from this is that all of your TLSs are Ta3+. But now in order to disentangle all of these things, you need to independently vary each of these parameters, right? So we need to now go and do a lot more different surface conditions. Okay, so that was sort of a deep dive, I apologize. But maybe the takeaway message here is that we had an enormous leap in performance from just trying a new superconductor, right? And sort of charitably, the superconducting qubit community had tried like 4 or 5 different metals for their superconducting qubits, and we added 1 and managed to move the state of the art by about a factor of 3. So I can list another 20 superconductors that you can kind of easily deposit in thin film and fabricate. So I think it is now time to start doing the more systematic search through material parameter space. For tantalum specifically, our current devices are both TLS and bulk loss limited, which I think is pretty interesting. Also kind of lousy because it means that you have to solve both problems. If you only solve one, you can only increase your Q by a factor of 2. And we're now interested in, because we can see that we're limited by TLSs, trying to understand the dynamics of these TLSs in more detail. Okay, so the shallow NV work that I talked about, the covariance sensing was led by Jared Rovney, and then a lot of the earlier shallow NV work was led by Leela Rogers and Peace Sunk-Tuason. And of course, as I mentioned earlier, the covariance sensing was all done in collaboration with Shimon Kolkowitz's group at Madison. The superconducting qubits work that I discussed was led by Russell McClellan and Avik Dutta in my group, and Kevin Crowley and Alex Place in Andrew Hauk's group, and of course was done in collaboration with Andrew Hauk and Bob Kava. And then a lot of the chemical profiling work that I talked about was done in collaboration with a large number of scientists at Brookhaven National Lab, especially Andrew Walter, who's at NSLS2, and Mingzhao Liu, who's at the Center for Functional Nanomaterials at BNL. And there's a large number of funding agencies to thank. I should especially point out our DOE NQIS Center, the Co-Design Center for Quantum Advantage, which has been really wonderful for me in terms of getting access sort of immediately to the enormous wealth of knowledge at Yale. I have Rob and Michelle in a Slack channel to tell me when my ideas are stupid, and that has been great for moving really quickly. And then just by way of advertisement, I just wanted to say that it's a really exciting time for quantum at Princeton right now. We launched the Princeton Quantum Initiative a few years ago. We currently have junior and open rank quantum searches. We have a postdoctoral fellowship that with a due date in the fall, and we have an undergraduate research program that is in collaboration with IBM. And then very, very quickly, I've also started a diamond growth effort together with the Princeton Plasma Physics Laboratory. We are currently hiring many staff research physicists there. And I'd be happy to take questions, and thank you so much for your attention. Yeah.
Thanks. Thank you very much. Very nice talk. I would like to zero in maybe and ask you about some of the tantalum work. And so maybe let me preface this question by saying that I grew up in a world that has a very large love for aluminum. And you have thoroughly convinced me that tantalum is better than niobium for maybe many of the reasons that you show. But can you talk to me about aluminum and aluminum oxide? I'm always told the oxide is self-limiting. I hear some of the same words, and maybe can I say that the reason that your qubits are better than the rest of the history's qubits are more about your surface prep and care that you learned from diamonds as opposed to the pick of tantalum over aluminum?
Yeah, it's a good question, and I think it is still not settled. But I will tell you my best guess. So I think the main reason why tantalum is better than aluminum right now is that aluminum is very hard to process. Once you have the aluminum down there, you can't stick it in anything. It's a total wilting flour. You can't do any acid processing or base processing or anything. Whereas the tantalum, I just told you, we boil it in sulfuric, nitric, and perchloric acid for an hour and a half. And the only thing that happens is that the oxide grows from 2 nanometers to 4 nanometers, right? So it's incredibly robust to anything that you want to throw at it. So I think a very large fraction of the story is probably just that a lot of the aluminum devices are still just limited by fabrication residue and hydrocarbons, and those are very hard to remove without destroying the underlying aluminum device. So this is one of the reasons that I'm really interested in new Josephson junctions, because now if you can make a Josephson junction that is more robust to that kind of chemical processing, maybe you really win. I will say, and I hope that I'm not going on too much of a limb, and I'm sure that Michelle will yell at me later, that my other deep suspicion is that aluminum has a non-equilibrium quasi-particle problem. Because when people do power dependence and temperature dependence on aluminum, it doesn't look that TLS-y. So my feeling is, you can do the measurements and fit your data and see if it looks TLS-y, and they see that it kind of doesn't look that TLS-y. So I have a deep suspicion that non-equilibrium quasi-particles play a big role, but of course now you're in this horrible regime where like exactly how your fridge is buttoned up and what your packaging looks like and all that stuff is going to really change from one person's measurements to another. But I think this kind of parameterization that I outlined is critical for making these kinds of comparisons. So I would like it if the communities just started doing exactly this, right? like a lot more resonator measurements that we could quantitatively compare.
Okay, thank you.
Thanks for a great talk. So just asking and like stepping back to get your big picture view about surfaces. Like surfaces are just difficult, and you started off by saying this. What is your sort of sentiment of like the prospects for actually getting, you've done really amazing work, hard work, gotten factors of 3 or 10 or something like that. Are there more factors of 10 to be had somehow? How does one keep moving the ball?
Yeah, this is going on YouTube. Well, okay, so what I would say, I don't want to keep on, sounding the exact same thing over and over again on my soapbox, but like the key thing is parametrization, right? So in NV world, I think no progress was possible until we generated that plot of coherence time versus depth. And then now having that plot allowed other people to go make measurements, sparse measurements, and then say we can improve or we haven't improved, right? So I think this, my attempt to do this on the superconducting qubit side is, is basically this plot, right? So now if you, and we're following a playbook here, right? Like lots of people have done the surface participation ratio thing, but I think the difference is that we're extracting a parameter. So instead of just looking at Q, you have to pick out the thing that is actually related to the material system. Okay, so that's the first, that's step one. And what this allows you to do is disentangle where are my losses. And what this tells you is that if you thought that you were living in a world where it was all surface TLSs, and then you just did a bunch of random things to the surface and then tried to measure devices, you would have failed, right? Because up here, you would have found that you were just bulk limited, but not 100% bulk limited. Up here, you sort of have equal contributions from the surface and the bulk, so it would have been very hard to detect. Okay, if I have to plot the course forward now based on this plot, I would say this is interesting because this loss is about an order of magnitude higher than what Rob has measured with the dielectric dipper. And even though we're looking at the same sapphire nominally, so one possibility is that you're actually dominated by a damage layer near the surface of sapphire that comes from polish damage or something like that. That's about 1/10 of the total thickness of the sapphire. So to me, this is like a very nice story because this is just like the diamond thing, right? We have to worry about this polish damage and figure out how to deal with that. But then this surface thing, right? We think that it's oxides and hydrocarbons. I kind of know how to deal with hydrocarbons. I don't want to build a cluster tool, but we are probably going to get there eventually. But with the oxide, I think the obvious next thing to do is to try to not have an oxide, right? So there's lots of ways to passivate. Nobody has really tried. That's where I would go next.
So you said you weren't going to be that sheriff that came into the room and fixed everyone's TLS problem, but sort of did do that.
Trapped ions?
Yeah, exactly. So I mean, like, is there the possibility of trying to do analogous tests with trapped ions?
Yeah. Okay, I haven't thought about it that hard. I should say, because I'm aggressively trying to not think about it.
Well, you'll be at NIST tomorrow. So, yeah.
But actually, we do have like a proposal out right now for an NSF center where part of the value proposition is that they're linking me up with the trapped ion people at Duke so that I can tell them about surface spectroscopy and stuff. So maybe I'll get nerd sniped into this topic too. So the problem that I see with trying to do the same thing with trapped ions is that you have to trap ions. and I don't know how to speed that up, basically. There's probably a way to speed it up. You could probably design a chamber where you could swap things in faster, but I think that's probably the big thing that's missing in the field is a way to rapidly prototype and do measurements.
But at the same time, it seems like the key thing here was actually figuring out the surface science even before doing measurements on the qubits.
Yeah, that's right. So I will say, this is going on YouTube, so I should be careful. But but I think one approach that I would caution people from is building a big surface science experiment inside your tool, because I think if you do that, the problem is that you don't actually know if you have the right surface science, right? It's very coarse. You're sort of prejudging that you can learn everything that you need to learn with LEAD or Auger spectroscopy or whatever it is that you put in there, because you're not going to have 50 experiments in one experiment. So I do think there's probably a lot of low-hanging fruit, which is like just taking microfabricated traps and then just sticking them through this big suite of surface science experiments and just seeing what's there. I think like people can't even tell me what's there. And I'm just sure that there's hydrocarbons everywhere. There's just no way that there aren't. If you haven't worked really hard to get rid of them, then they're definitely there. And even if you think that you're baking them off in vacuum, I've seen enough syndromes. Okay, let me tell you one really quick story and then I will get off of my soapbox. The big key enabling thing in diamond is that if you have any silicon-containing polymers on the diamond and you do any of this thermal processing, you form a silicon carbide and it's impossible to remove, and then you're just screwed. There's no way to get rid of it. There's no way to remove it in situ, and it's an enormous spin bath that makes all the end. So the key enabling step there was realizing that gel packs are bad, a lot of gloves leach silicon-containing polymer everywhere, a lot of containers that shouldn't have silicon in them. Basically, the way that they make things not stick to each other when they package them is by putting PDMS-like things all over them. So getting into a regime where we know what packaging stops you from getting the silicon-containing stuff, then allowed us to do the in situ processing that gets rid of the remaining hydrocarbons. So that's what I mean by if you build all of your surface science into your experiment, you've prejudged that you already understand what's wrong with the surface. So I think there's probably a lot of pre-work to do, which is just look at what's there, try to get rid of everything that you can, and make things as like smooth and clean and nice looking as possible. And the other thing that I've learned, especially from the superconducting qubit stuff, is if it looks lousy, it is probably lousy, right? So if it looks good, it's probably still lousy, but you know that it was much lousier if it looked lousy. So I think that there's a lot of like really basic, like just take a look at what it is. That as far as I know, again, I haven't looked very deeply into what people have done in this community. As far as I know, people haven't really done. I think they've mostly been looking at ions and just measuring their ions.
Thanks.
Thanks again for the very nice talk. So you mentioned like a lot of interesting techniques to get rid of surface contaminations. So I think in the community of XPS, at least people routinely use argon sputtering to remove hydrocarbon contamination. But I don't think you mentioned that, or does that leave like any uncontrolled damage or something?
Oh yeah, it definitely damages the heck out of your surface.
I see. So it gives you like not good results.
Yeah, I mean, we haven't really tried it with diamond. My bias here is that the best thing that you can ever do for low damage processing is wet chemistry and thermal annealing. And I think if you have some combination of those two things in all of your processing, then you're just golden. Anything that you introduce that's like a plasma or a physical sputtering step, you just have no idea. You just have no idea what you're left with. And it can be extremely complicated to disentangle what you might have done with that plasma. So it's not that it's impossible, it's just that it's very hard to figure out.
Thank you.
Thanks.
Yeah, I have a question about your energy-dependent photo emission on the tantalum. Do you have the same measurement on niobium, just to compare? I'm curious what they look like.
Yeah, so I should have had that on a backup slide. I do not, but Andrew's group actually had a previous collaboration with VNL to do a similar measurement. And it was before we figured out a lot of this curve fitting, so I would kind of like to revisit some of that data, but it's much, much messier. So, you know, in our depth profile, you can see that all the oxide is here, and then there's this interface layer that, you know, is maybe just a nanometer or something. And in niobium, on this scale, I think for many niobium devices, you would have your oxide is out to like 10 nanometers, and then this suboxide interface layer is like another 10 nanometers.
Okay, so
it is drastically different.
More of NB205 and everything else?
Yeah, that's right, and lots of different suboxides. I mean, I should mention the IMEC group has this very nice result where they took niobium resonators, dipped them in HF, got them in the DIL fridge as fast as possible, and they also see Qs of like 5 billion, right? So I think that's very good indication that the whole problem was with the oxides. The problem is that then you try to do any fabrication and you grow back these oxides in uncontrolled ways. So it's sort of a dead end for niobium.
I'll just chime in on behalf of the beleaguered ion trapping community that there are a few groups out there, including ours, that are trying to do basically surface studies on traps as well as using ions to measure them. But it's not as advanced in terms of really understanding deeply what's going on as what you've done. But it's definitely like we're trying to do that same sort of thing, and it'd be great to get your perspective on it offline.
So alas, at some point the university will take us away, and that point is not so far away. Maybe just one last question, if there is one. With that warning to all of you, apparently we decided to hold till after. Let's thank our speaker once again.